All right, buckle up, math enthusiasts. Today, we're not just going to state the Pythagorean theorem. We're going to see why it's true, not through some abstract manipulation of lengths, but through the beautiful language of area itself. Forget about a squared plus b squared equals c squared for a moment. Let's think about real squares. Imagine you have two squares of any random areas. One has a side length we'll call a, and the other has a side length b. Now, the Pythagorean theorem, at its heart, isn't really about the lengths of the sides of a right triangle. That's why we must get to know what problem the Pythagorean theorem actually solves first. Then we get to know what its true meaning is. It's actually about the areas of some three random squares who by some chances have their sides making out a right triangle. Think about it. Most formulas in the real world involve squares and cubes, area and volume. That's how things manifest. So it makes perfect sense that this fundamental relationship in geometry would also be rooted in the concept of area. By the way, maybe fourth powers and the rest might also manifest in life in a way no one has discovered. Who knows? Now here's the puzzle. If we have these two squares with areas a squared and b squared, how do they relate to a third square built on the hypotenuse of a right triangle formed by sides a and b? Let's take a look at this construction. We're going to build a larger square. Imagine taking the side of length a and the side of length b and arranging them to form a larger square with a side length of a plus b. The total area of this big square, well, it's simply the quantity a plus b squared. But within this larger square, we're going to cleverly arrange four identical right triangles, each with legs of length a and b. Notice something interesting here. The hypotenuses of these four triangles form a central tilted square. Let's call the side length of this inner square c. Its area, naturally, is c squared. Now let's think about the larger area. The area of the large outer square must be equal to the sum of the areas of the four triangles and the area of the tilted square. Each of those right triangles has an area of 1/2 times its base times height, which is equal to 1/2 times a times b. And since there are four of them, their total area is 4 times that, which is equal to 2ab. So we have area of large square equals area of inner square plus area of four triangles. That is, the quantity a plus b squared equals c squared plus 2ab. Let's expand that left side. We get a squared plus b squared plus 2ab. And now the magic happens. We have 2ab on both sides of the equation. Subtracting 2ab from both sides, we are left with a squared plus b squared equals c squared. Boom. There it is. The area of the square built on one leg, a squared, plus the area of the square built on the other leg, b squared, is exactly equal to the area of the square built on the hypotenuse, c squared. So, you see, the Pythagorean theorem isn't just some abstract rule about lengths. It's a fundamental relationship about how areas combine in a beautiful and predictable way. By visualizing these squares and how they fit together, we gain a much deeper understanding of why this cornerstone of geometry holds true. Join our WhatsApp channel for more mind-blowing proofs.